Okay, so good evening to all of you once again. In today's class, we are going to learn a little bit about static timing analysis of sequential circuits. Okay, even in the testability course, which many of you have enrolled, I mentioned that we need to do an static timing analysis post routing. Right, once you do the placement and routing, and we have the clock circuit also, the clock circuit which is feeding the clock to the various flip-flops within a chip. When even that is done, post that we will do an static timing analysis. Okay, so why do we need to do a static timing analysis? How to go about doing static timing analysis? That is all we are going to learn in this particular class. Okay, so this is like for a flip-flop, we said there are three figures of merits which we should know, and for various flip-flop designs we learned that how to compute the setup time and hold time and the propagation delay. So what's a setup time of a flip-flop? We said that the data which is there, like this graphs is shown for a D flip-flop. So the data needs to be stable. The input data needs to be stable before the arrival of the clock. Okay, and that duration for which before which the data needs to be stable is known as setup time. Now, if this is the clock arrival time, and if the data is going to change within this setup duration, then this data may not be captured correctly, right? So for this data to be captured correctly by the flip-flop, it is necessary that data gets stabilized before a duration of this T setup. Okay, and that is the time that is before the arrival of the clock. By a time period, by a time known as setup time, the data needs to be stable. Similarly, once the clock goes high for various flip-flops, so these are the properties of the flip-flop. So various flip-flops will have various kinds of setups and hold time. So hold time is once the clock goes high, you can't change the data immediately. You need to keep the data stable for a certain amount of time. Okay, otherwise the data could again get corrupted. Okay, the flop could become transparent during can remain transparent during this whole time, right? So that should not be there the case. So we saw all these constraints coming from the flop design. Okay, so these are setup time and the hold time. Okay, and then we also defined something known as propagation delay. That is assuming that okay, this setup time constraint is already met. Then once the clock goes high, then from there onwards the output data will be available. Stable output data, desired output data will be available after a time known as the propagation delay of the flip-flop, that we generally call T C dash Q. Okay, from the clock till the Q is output, Q is available. Okay, Q not necessarily means Q. Q means Q and Q bar both are available by that time. Okay, so so generally Q bar together we call it as an Q here. So these are the three figures of merit associated with the flip-flop. Now, what's a clock skew and clock jitter? Okay, clock skew is sometimes it's known as a timing skew. This happens because the clocks they reach different flip-flops at different times. Okay, the reasons could be wires and buffers, right? So each flip-flop between two flip-flops, okay, the wire length could be different from the source of the clock, right? So they could be there could be one flip-flop here, there could be a second flip-flop here. This could be a clock buffer, so it could come here like this, and the same clock is coming here, right? So whereas because of this wire, okay, lengthier wire out here, right? So the resistance and the capacitance associated with this lengthier wire will cause a delay in the clock coming here, right? So that can cause clock skew. Also, when we do the routing and placement, there could be buffers in between. Okay, many buffers in this clock, because there could be some distribution like this, right? So this clock is coming directly here, whereas in this path, and there could be the clock might be going to various flip-flops in the to the various flip-flops within the chip. Okay, so there could be some clock distribution network, and there could be additional buffers placed in between. Right, this again we saw in that last class in the clock distribution system. Right, so again in this case also, because of the buffers which have been inserted in between, each buffer might have some specific time delay, so that can also cause an net difference in time in the clock timings, right, which is reaching here and which is reaching here. So these things can cause clock skew. Okay, and there could be something known as clock jitter. Okay, jitter is because we studied about PLL also, right? So all those PLLs, and we had an right, and quartz crystal and all. So there could be some noise which is coming from those PLLs and also, right. So that means there could instead of having an right clock at this edge and at this particular point of time, and it could vary here and here. It could vary because of temperature variations and also, right, from this is the main clock itself. So for a given flip-flop itself, there could be some variations in the clock. Okay, that is known as jitter. So the total clock uncertainty is sum total of the jitter and the skew. Okay, so now coming to the timing constraints of an flip-flop. Okay, suppose this is an ideal clock, right? Now this is a clock with jitter. Now what is happening is the clock is arriving slightly ahead of its time. Okay, because of jitter, or right, because of unequal because of skew also it can happen. We'll see what the positive skew and the negative skew. So because of in general I can call it as because of clock uncertainty. If the clock is arriving early itself, okay, what can happen, like the setup time, like in this particular case, okay, had the clock come in the correct time, there was adequate time available, right, for the setup. Okay, now because the clock is arriving early, right, and so this data is changing here, so there is no adequate time available for setup. So this can cause an data setup violation. Okay, so can I say that a clock coming early, right, into the capture flip-flop where the data needs to be captured, right, will cause setup violation? Is this
Yes.
yes?
Yes, sir.
So a clock which is coming early into the capture flop can cause setup violations. Okay. Now the clock can come late also, right? So it is not necessarily clock can come early. So because of jitter and skew can be on the either side, right, positive or negative. So now here, if you see here, this is the actual clock and the data is changing out here, right. So between these two edges there is an adequate time available to meet the hold requirement, right. But no, here it is changing and the data is changing out here, right. But whereas here, if you see here, now this clock is coming late, right. So from here to here, right, there is no the data is here. If you see here, this is the clock which is changing, and the data is changing. Had started changing somewhere from here, from this end. So this much time was available. Okay, so whole time is met. Now the clock is getting delayed. Okay, now the clock is getting delayed. Now that now because of which data is changing here and clock is changing here. Now there is no adequate time, whole time available, right? So can I say that arrival of clock, late arrival of clock to the capture flip flop can cause whole time violation?
Yes, sir.
Okay, so these are the two things which we need to remember, right? So like this we discussed. Why should there be clock mismatch? Because if you see in this particular circuit, okay, there are several buffers which have been inserted. Okay, so this is the longest path. Okay, this particular flip flop. So when you make a VLSI chip, so there could be many buffers, and the length of the wire, okay, also is different, okay, from flop to flop. Length of the wire which is bringing in the clock to that particular flip-flop. So a wire mismatch, difference in the input capacitance of the clock, varying number of buffers in the interconnect. So all these things will cause an skew, okay. So there could be a positive skew and a negative skew. Okay, positive skew means the capture clock. Okay, this data, this is the capture flip flop. Okay, where the data needs to be captured. This is known as the launch flip flop, because this data is coming from here to here. Okay, now we are analyzing this particular circuit. This data is coming from here to here, right? So here this clock is coming delayed into this flip flop. Okay, so this is known as positive. So positive skew, what kind of violation will it cause? Hold violation or setup violation?
Setup. Hold violation.
Hold violation, because the clock is coming late, right? The clock is coming late, so it can cause hold violations, okay? And there could be negative skew also. So this is the capture flip flop and this is the launch flip flop. Here you find the clock is late here, right? Here the clock is coming early, okay? So here the data is getting is coming here at the output slightly late. So there is not adequate time available for the data to come here, and hence negative skew can cause hold violations. Okay, so depending on the circuit, right? This is a physical layout. Okay, so so whatever reason, when we make the layout, and it is possible that there are more buffers here and right, and less buffer in this path. Okay, so that depends on the clock distribution circuit. Okay, the clock might be taken from this side of the chip also during the layout. So the capture flip flop may have a lesser clock delay and than the launch flip flop. So that can happen. So we need to check for all these things in our static timing analysis. Okay, so these are the few things which we need to remember. Now there could be two main problems that can arise in synchronous logic. Max delay. So that means the data doesn't have enough time to pass from one register to other before the next clock edge, and so this can cause right, the setup violations. Similarly, minimum delay, that is the data is moving too fast. Okay, so that also can cause hold violations. Okay, so both of them are a problem. Okay, now even if the data is moving too fast, then also it could be a problem. If it is too slow, that is also a problem. So data in the data path, if it is too slow, then it could cause setup violations, and if the data is too fast, okay, then it can cause hold violations. Okay, so this is with respect to data. The last two slides we saw with respect to the clock what is there, right? So we have to take into consideration, okay, finally for an STA analysis, we need to take into consideration both the clock path and the data path. Okay, and then analyze whether there is any setup violations or hold violations. Okay, so this is like for a setup constraint. Okay, so this is known as the launch path, where the data is launched, and this is known as the capture path. Okay, now when I'm what is setup constraint? How we do it? Like we are giving one clock here, right? So this data here which is available, so this data of this flip flop will be updated, and there will be some combinational block in between that will do the compute the new value of B, right? And it will be offered out here as an input to the next flip flop, that is the capture flip flop, right? And that data needs to be captured in the next clock, right? Not in that clock. That's how this works, right? So between one clock and two clock, this data needs to traverse like this here, and it has to get settled here, right? So can I write this equation like this? The time period, okay, between this and this has to be TCQ of this flip flop, right? Flip flop 1. So this corresponds to a flip flop 1, right? T logic, there is only a single T logic in this particular. So, and T setup. What is this T setup of which flip flop? Can anybody say this flip flop or this flip flop?
Capture flip flop.
Yeah. So this, okay, this F2. So F2, right? So this is the timing constraint which we need to analyze. Okay. So so if T is more than this, so I do T minus this, okay, and if it is positive, then I can say it has got some positive slack, okay, that is known as slack, okay, that means there is some right slack is available, which is good, right? So no time. But if I do this minus this and I get a negative result, that means there is a timing violation. That means the setup violation. There is a setup violation, right? So this equation can further be modified, right? There could be some clock skew, right? Here this clock and this clock, right? I am assuming that there is no delay in this path, okay? But there could be some buffers in between, right? So that will add additional skew out here, right? So if this clock is coming late out here, okay, by some delta, can I add that delta here? Because that much more time is available for this data to transfer here, right? So if there is some delay out here, right, positive skew, can I add that here? Right, data can take that much more time, right, because the clock is delayed. So I have that much more flexibility. So can I add one delta skew here?
Yes, sir.
Yeah, okay, so that is done there, right? And then you might want to add some margin, 5%, 10% margin in your design, okay? So so when you do this minus this, that will give a positive slack, okay? So I'll give you an example where we compute the slack, okay? Then it will be, things will be more clear to you. Similarly, I can have an hold constraint, okay? Now, a hold constraint is nothing to do with the clock period, okay? Setup constraint, okay? Setup constraint is not, for a circuit, I simply cannot see a circuit and tell whether there is a setup constraint or not, because the frequency, it depends on the frequency. So there is a T involved in the computation of setup constraint, right? Like, whereas for the hold constraint, there is no it's nothing to do with the time period, okay, switching operation. Now, because I am giving a clock here, I am giving a clock here, right? So this data is coming from here to here to here, okay? So this data should not change at B, okay, till my hold time expires. Correct? So it is nothing to do with the clock, with the same clock edge. Okay, I am giving the same clock edge here, right? So this delay from here to here and this delay, okay, should be greater than T hold. That means this data should not change till my hold time requirement of this flop, the second flop is over, till that hold time expires, right? So this is nothing to do with clock. Okay, so this doesn't put an does not impose a restriction on the frequency of operation, whereas this is going to impose an restriction on the frequency of operation, right? If I am saying T has to be greater than something, that means the max frequency gets restricted here, isn't it? Yeah, Mrityunjay, Gokhale, agree?
Yes, sir.
Right, okay. So whereas here, okay, this condition needs to be met, okay, only. So this is there is no time period, clock time period involved here, right? So this is the equation. Now in this case, if the clock skew, if the clock is coming delayed here, right, that means it's a bad thing, right, for me, right? So I need to add that particular skew also along with the hold time, right? Because so hold time in fact increases because of the clock which is coming delayed here, right? And then you could put an delta margin if in the design, if you want, you can do that, right? So now again, data arrival time minus data required time will give the hold slack, Okay, positive slack, you have to check for positive slack, that means it is fine. Negative slack means there is an timing violation. Okay, so these two, how to compute these two slacks will be clear with one example which I will discuss. Okay, so the launch path, okay, these are just the definitions, you can just note down. Launch path is the launch clock path, okay, which is responsible for launching the data at the launch flip flop. Okay, a capture path is the capture clock path. Okay, for now arrival time is the launch path and the data path together, because finally the data needs to come to the capture flop, and required time is what is the actual required time. Okay, so these are some of the definitions. This example will with this example your setup time and hold time concepts will be very clear. So just listen to this carefully what we are doing. Now setup slack. Okay, for the setup slack, okay, first we need to find the minimum clock path delay. Okay, now for each of these, now like this is a wire coming from here to here, right? So after the layout, and I can say these are the minimum delay which is there in this particular wire. Okay, 1 nanosecond, and maximum delay in this wire is 2 nanosecond. Similarly here, okay, for the flip flop 1, right, the minimum delay from clock to Q is 9 nanosecond and maximum is 11 nanosecond. Okay, so these data are available to us. Okay, for it will be available to the tool also. So this is the minimum delay, max delay. Okay, similarly for this inverter, there could be a minimum delay, maximum delay, minimum delay, maximum delay. This is for the wires. Okay, this is for the wires, and this particular flip flop, hold time and setup time is given. Okay. And now hold time and setup time, minimum maximum is not given. Okay, it is one single values which has been given out here. Now to find out the setup slack. Okay, now for the setup slack, I need to consider the worst case scenario. So for a worst case scenario, should I consider fastest clock path or the slowest clock path?
Fastest clock path.
Yeah, fastest. Okay, so now this clock, okay, so 50 nanosecond is the time period, okay, available for this data to get settled here, right? One time period is also available, right? So one time period is available plus fastest clock, okay, 2 nanosecond plus 5 nanosecond, okay, and 2 nanosecond, right, minus 4 nanosecond, which is the setup. So this data needs to be settled here, right? Once I have triggered this particular data path from here to here, okay, this is the clock path. So the data path, okay, the clock path, the fastest time the clock will reach here, okay, and from one pulse to other pulse, okay, at a time t is equal to 0, I have triggered this, right, and now the second clock is coming, okay, at after time period t. So that clock edge is going to come here. Before that, this previous data which was triggered here, that needs to come here. Okay, so we are going to compare those two. So I have 15 nanoseconds, that is the time period. 2 nanoseconds, which is the fastest path. Since I am talking about the worst case scenario, I am taking 2 nanosecond here, 5 nanosecond here, 2 nanosecond here, and also the setup time. Okay, so setup time I am taking it as negative, because I need to this data needs to settle before the right setup time. So that much time is actually not available, so I have to cater for. So this is negative, right? And what about the data? Data I will take the slowest path. Okay, so worst case scenario needs to be checked. So slowest path is 2 nanosecond. Here it is 11 plus another 2 plus 6 plus 2 nanosecond, right? So now if I subtract these two, I am getting as negative value. That means the setup slack is negative. So there is a setup time violation, right? So if I use t is equal to 15 nanosecond, right? So there could be an setup time violation, correct? There will be a setup time violation, worst case scenario. Is this okay with all of you? Is this calculations
After
and
the clock,
yeah, tell me.
after the clock, it is 1 nanosecond, 2 nanoseconds. You told this minimum is 1 nanosecond, sir.
Yes.
15 nanosecond plus 1 nanosecond. It should be all 2 times.
Pardon, time period is
50
15
nanosecond.
nanosecond.
After this,
This is
minimum is
this is the wire delay.
this.
Okay, this is a different wire.
Okay.
This is so these are the wire delays which have been mentioned here. Is it okay?
Okay, sir.
Okay. Now, so this is not a very good situation. So, what can I do? Tell me.
Delay clock by
Delay
some
clock
amount.
by what should be T?
21.
22.
Why 22? Why can't it be 21?
Some margin.
No, yeah, if you don't consider margin, okay. So if I give this circuit and tell you to compute the max frequency, right? So the max frequency, if you compute, it will be right 15 plus another 6, right? So 21. So 1 by 21 nanosecond will be the max frequency of operation of this particular circuit. Okay. So either you reduce T, or can we do something else also? What are the other options available?
We can take a different inverter with less max delay.
Yes. Right. So
We
other
can
option.
reduce the delay bit.
No, like you could reduce the delay in the data path. Okay, you can choose a flip flop which is faster. You can choose an inverter which is faster, right? Okay, that could be a slightly tricky issue. We may not have. What could be an easier option?
Frequency.
A frequency. Maybe I don't want to change the frequency, right? I would want to operate at this frequency. Then?
Buffer the clock path.
Yes. Can I insert a buffer here?
Yes.
Yes. Okay. So that could be the most best thing to do
But-
in this particular.
But hold margin is less only one
Huh.
T, 1 ns.
Yeah.
Hold margin. Yes. So you have to ensure that there is no hold time. We'll talk about that. Okay. Now coming to hold time. Okay. Hold time is like this is being this clock is given here and clock is given here, right? Now we are telling the clock has to be delayed, right, from here to here, right? Now if the clock is clock minimum data arrival time is now we are going to talk about max delay in the clock and minimum delay in the data, other way around for the worst case scenario. So minimum data travel is now it's about the same edge. Okay. So in the same edge, okay, by the time the clock is coming here, the data should not change here. Okay, same clock. We are not talking about two different clock edges here, right? So now this clock we have triggered here. Okay, so let's see what happens to the data. So fastest way the data can change is 1 nanosecond. And here it is 9 nanosecond, and then another 1 nanosecond here in this wire, plus 6 plus 1 nanosecond, right? And this is the fastest way the data can change. Okay, so meanwhile what happens to the clock? Let's take for the worst case scenario, we take the slowest path. So 3 nanosecond and 9 nanosecond, 3 nanosecond, and then the whole time requirement is also there. So you take, so 1 nanosecond is the a hold slack which is available here. So there is no hold time variation, right? So here I guess so one option is to insert a buffer out here, but if you insert a buffer here, I think there will be an hold time violation, correct?
Yes.
Yes.
So there could
Yes,
be
yes.
here there could be a hold time variation. So you have to see what is the best available option. Okay, so you have to see all the constraints and accordingly do that. Right now for this circuit, okay, what is the max clock frequency? There is a flip flop here. There is some combinational logic, and this output is again fed here, right? So the time period, okay, is an T flip flop. T propagation flip flop is from the clock to here, right, plus the logic plus the setup time. So this is the max minimum time. This is known as the T minimum, right? So F max will be 1 by T minimum. Okay. So is this okay with all of you till here? Okay.
Yes, sir.
Okay. Now for this particular circuit, given the data
Sir, can
setup,
you repeat
this one,
last slide?
this
Yeah,
one.
yeah.
See,
Yes.
what is the max clock frequency of this particular circuit? If these three values are given, setup time is given, combinational circuit delay is given, propagation delay of this flip-flop is given, and the setup time is also given of this flip-flop, and the delay in this combinational block. So when I give one clock out here, right, before the next clock comes, okay, this data needs to travel from here, right? So this is it has to travel here, and it also has to cater for the setup time of this flip-flop, right? So the next edge of the clock, okay, before it comes, you should cater for these three timings. So this will give the minimum time between two edges of the clock. So F max, okay, will be 1 divided by T min. Is it okay?
Yes, sir.
Okay. Right. Now for this particular circuit, you have another circuit here. This is like now you give Q bar. This is used to many times in the combinational circuits when I have to divide the frequency by 2. This is I can do, right? This is the input frequency. This is the output frequency. It will be exactly a half this, okay? Because if you see here, every time the clock comes, right, Q bar. So in the next clock, it will be set to Q bar, right? But if you analyze the waveforms, it will be this F in and F out. F out will be half of that of F in, okay? Now, what is the maximum clock period required to handle the circuit? Okay. Now these data are given. Okay. Setup time is 6 nanosecond. Hold time is 2 nanosecond, right? And the propagation delay here is 10 nanosecond. So what is T minimum?
16 nanosecond.
T minimum is 16 nanosecond. All of you agree with that? Because once this clock goes,
Yes.
this data has to come from here to here, right? So please don't like in many circuits when we talked about flip-flops, okay, there is a small amount of delay between Q and Q bar itself, right? Q bar might be coming slightly early or slightly later. So let's not get confused with that, okay? When we do and ultimately when we take flip-flop as a single block, we don't try to distinguish between Q and Q bar, okay? So the flip-flop data we will assume both Q and Q bar are available at a time given by TCQ, okay? So this is available, and then that needs to come here. So setup time also you need to. So T min has to be
18.
greater than or equal to 16, correct?
Yes.
Correct. So
Yes.
so the frequency will be 1 by 16 gigahertz. Okay. Right. Okay. Now, is there any hold violations here? Just can
No.
right? Because see the hold time required is 2 nanosecond, right? So once I give an clock out here, right? By the time the data gets changed here, it is 10 nanosecond, right? So this data remains stable for hold time is 2 nanoseconds. So there is no hold violation here, right? So T minimum is 1 by 16 nanosecond, right? This 1 by 16 nanosecond, which comes out to be 62.5 megahertz. Okay, and there is no hold violation in this particular circuit. Okay, right? Now, when we come to when we manufacture, okay, flip flops, when we do VLSI chip fabrication, then there could be a different locations and different gates can have different delays, okay, different performance, right? Because the T ox of the MOSFETs involved can change slowly, which can affect the total current capability of those things, okay. So so that is one, or the doping can slightly change, okay. Generally the thickness of the oxide and even a small marginal difference in the chip in the during fabrication in the T oxide can change the VT. VT in fact will change the total current and which is available, and so these are known as on-chip variation, okay, OCV variation. So so our when we do an STA analysis, okay, sometimes, okay, though so here we said here if this data is available, right, okay, a max and min max min max min max min data is available, okay. So sometimes that max min data will not be available, okay, in some circuits. It will be like the nominal delays will be available, and then we have to consider, okay, for a particular technology the OCV variations is 10%, 20% and 30%, whatever, okay, depending on what the fab lab says you, okay. If the fab lab says, okay, we are a very good fab lab where only 5% is the OCV variations in our chips, okay, then you could do an ST analysis with 5%, okay. Probably if they say, okay, it is 7%, and maybe you want to be very sure, okay, you can add another 3% and keep it at 10%. It's up to you. So so this when we do the ST analysis, okay, with OCV technique, okay, the tool would ask you, okay, what kind of percentage you need to set, okay. So you will give that percentage to the tool, so the tool will apply that percentage, okay. Now for a worst case scenario and right, what it does is, okay, in the launch path it would make it 10% faster, okay, and so the and for the hold it will make it 10% slower, okay. So worst case scenario, so it will take that worst case scenarios. Now it will be very clear in the example which we discuss here in the next slide, right. Suppose here only the nominal values have been given here, okay, max min values are not being given here. So for the setup slack, okay, first I take the clock path, right. So here 100T, have I written 100 as the clock speed? No, right. I need to write that, right. So let's assume the clock period to be right. For STA analysis, right, especially for the slack and the setup analysis, setup slack analysis, the time period needs to be specified. Without that, you can't calculate the slack, okay. You might be able to compute the total setup requirement of the system, but slack will not, you cannot compute unless the time period. Now the time period is specified. So time period plus what is the in the clock path, okay. So 10 plus 3 into 10 I have written. These are the buffers. So 3 into 10 minus the setup, okay, of this flip flop, because 30 is so this is 30, which is the setup requirement of this flip flop 2, okay. So and this here this is the data path, okay. Now in the data path also, for this data to get triggered, okay, first of all this clock has to path pass through these two buffers. So this 10 plus 10, only then the data will get triggered, right? So you have to take into consideration this also. So this is the total launch path. Okay, this is the capture path. Okay, so in the capture path, I have 1 buffer, 2 buffer, 3 buffer, 4 buffer, and the setup time. Okay, so these 3 buffers plus the this buffer, and also the time period, because this data needs to be captured only in the next positive edge. First positive edge, I have triggered the data. Okay, I have started a data chain. So that data chain needs to be stabilized before the next clock comes to this flip-flop. Okay, so that is why this 100 is also included here. Now here in the data part, 10 10, and this is 50. 20 is the delay of here, right? So I get this is the slack. Okay, 20 picosecond. Okay, this has to be pico, I guess. Okay, so this example is picosecond example. So this is the slack. Slack is available, right? So now I can say what is the max frequency here? Let me put this question now here, which I can operate.
TPS 1 by 8 TPS.
1 by
8 TPS.
Yes, 1 by 80 picosecond, right? This 20 slack is available, so I can further reduce the time by another 20. Okay, so it will be 1 by 80. Now let's do an hold slack analysis. Okay, here, like I said, in the hold slack, a single clock, okay, is given here. By the time the clock is coming here, the data should not change here, right? So now how is the clock traveling? 10 plus 3 into 10. Right, 3 into 10 out here, hold slack, plus the hold time is 30, correct? So that is what, so here it is 10 plus 3, right? So meanwhile, the data should not change. So I take this data out here, right? So it is 10 plus 10 plus 50 plus 20. So this is 30 picosecond. So there is no violation. So this circuit is good, fine, right? Now I have to do an OCV variation also, right? Suppose, okay, it says, okay, if they say, okay, flip flop, there is no OCV needs to be applied. If it says you need to apply OCV here also, then you could do that also. But let's take an example where all the gates, okay, all the gates, these inverters, okay, for which we need to apply a 10% OCV, right? So in that case, in the setup path, right, in the setup path, right, so this is the way this data is going, right? So for a worst case scenario, okay, I will assume that, okay, this is getting delayed. Okay, so what will I do? And I will say in the clock, this is going faster. So I will reduce the delay in the clock path and increase the delay in the data path by 10%. Okay, now if you see here, so 10 into C1, okay, plus these 10, okay, this entire thing I am going to multiply by 0.9. Okay, so this is I am making this slightly faster by reducing the delay only of the gates. Okay, now if I have to put that OCV on the flip flop also, then I can bring this 30 also into this bracket, right? So that also I can do. So it depends on what is the data with the coming from the fab lab. Okay, generally flip flops, they don't say, okay, they give this time, but for the gates they generally say, okay, you could apply. So I have reduced this as this delay in this path, okay, for the setup violation, reduced here by 0.9. And whereas in the data path, I am going to increase it by another 10%. Okay, so all which are there in the gate in this path, right? Now, all the propagation delays here, they have been increased by 1.1. Okay, only these the hold time and the setup time we have not applied OCV, right? The delay for the flip flops we have applied OCV. That depends on how the Fab Lab gives the data, right? So I have done that. So now I'll get some value which will be this is 20 picosecond. Now if you try to compute here, obviously the slack will be much lesser. Okay, there could be some violation also now if you apply OCV, right? So is the concept of applying OCV, is it okay with all of you? How to apply OCV on the setup? Okay, now when I see a worst case scenario, okay, so we have to slow this and make this fast, okay, because we ultimately what should be our aim, that when even if there is a variation in the chip, our chip should work without any faults, right? So if we design to cater for the worst case scenarios, okay, then if you start designing for the best case scenario, then most likely our chip will fail, right? Ultimately, so our reliability will go down, right? So that we should not allow that to happen. So generally, we'll always cater our design in such a manner that even the worst case scenarios is taken care of. Now for the hold slack, now first I will see this 10 from C1, and this is the data which is coming. Okay, fastest path of data 10 plus 10 plus 50 plus 20, right? Now I am going to make it slow, right? So sorry, I'm going to make it fast. I'm going to reduce that delay. So I'm going to put 0.9 here, right? And then clock I am going to make it slower. Okay, so that is the worst case scenario. So I have one clock, two clock here, one buffer, 4 buffers, right? And I am not applying that on the hold time. Okay, because some say for this particular problem statement, it has they have asked us not to apply OCV on here, right? If it says apply here also, then this also goes into this bracket. Okay, so this is what. So now you will get slightly lesser hold slack, right? There could be a violation also, I'm not sure. You have to do the calculations and see, right? So this is how we apply this OCV variations. Okay, so your tool will do this. Okay, if you are working on an STA tool, okay, so this percentage what you give is a variable that is in your hands. Okay, so how much do you want to give, that is generally based on the feedback from the Fab Lab. If the Fab Lab says, okay, I am confident of giving you with 5% OCV variations, right? Also that, or many a times, like you may not have even you are making a circuit, you may not have even decided what is the Fab Lab, and you have taken some GPDK file with some nominal values out here. In that case, you might want to take some arbitrary OCV percentage and do the static analysis. And finally, when the Fab Lab data comes, you might want to modify this. Okay, so this is known as on-chip variation. Okay, is it clear to all this concept? Yeah, tell me.
Sir, there will be a possibility of having a Q bar also with an other possibility of a circuitry again with this flip flop.
Pardon, can you just repeat the question?
Like my question is, sir, in this flip flop one, the Q is connected to other NAND gate, and
Yes.
again some circuitry is there.
Yes.
Again, there is a possibility of having a Q bar also having other possibility of
yes.
different circuitry.
Every part. See, you have to analyze if there is an hold and setup violation in each flip flop. Okay, there could be one.
Okay, but the
Like pointer option, like there could be one more flip flop here where this Q bar is going there, right, through some combinational block, and it is going here, right? So you will do the STA analysis with respect to each capture flip flops in the circuit. Okay, there could be multiple launch flip-flops and multiple capture flip-flops. So each this constraint of hold time and setup time is specific to each flip-flop, right? So for each of these flip-flops, okay, so these conditions needs to be met. Is it okay?
Yes, sir. Hello, sir.
Yeah, and the slack will be suppose you are doing an analysis. There different circuits might different flip-flops and different paths will have different slacks. So your max frequency which you decide finally has to cater for that worst case path. Yeah, tell me.
Yeah. For C1, sir, we have to consider this common path pessimism also, right?
I'll talk about
For
it.
C1.
I'll talk. I have not yet introduced common path pessimism.
Okay.
Okay, I'll talk about that. Okay. So let's take a break out here. Now it is 16:31. 16:41 we will meet and talk about clock pessimism. Yeah, tell me.
So one more question from my side was like basically, there was a clock path and data path, right? We will be having, right? But like for the OCV, how we can determine the 10% for which one, 10% we are subtracting and 10% we are adding. I mean, for the complex circuit, how we can determine that?
No, see, this is data path, right? For setup path, okay, we are no, this is the clock path. So for when we do the setup path, right, we will assume that the clock path is coming faster, right, and hence we will will decrease the delay, and hence we'll take that 10% decrease of 10%, which comes out to be 2.9, right, and data we will slow for the worst case scenario, right, and hence we'll increase it by 1.1. Right, the 1.1 is will cater for the 10% condition, right? 10%. Whereas for the whole slack, it's the other way around. We will assume that data is coming faster, and the clock in the clock path, whatever delay is there, that we are going to increase by a factor of 1.1. So this is 10, right? If it is in a 20%, then this 0.9 will become 0.8, and this will become 1.2. Okay.
Yes.
So the worst case scenarios will be catered, right? So these days the tool will do the analysis itself, and it will give the results. You just have to set these values, but you have to understand these concepts. Okay. Right, now let's consider this particular circuit. We said, okay, during computation of the launch path, okay, we take this particular path. So so for an setup thing, we take the max delay. Okay, so if it is 1 and 1.8, we take excuse me, 1 nanosecond. This is the worst case. Okay, 1 nanosecond. So we take this particular path, and for the clock path, obviously a time period has to be added, and then we take the fastest. Okay, 0.8. Okay, but this is actually we are being too pessimistic. Okay, the reason is once we fabricate, okay, these devices, okay, C1 and C2, okay, once it is fabricated, so both for one during one period during one edge, okay, this is 1 nanosecond, and in that next stage it will be 0.8 nanosecond. That can't happen, right? That probability is very, very less, right? Because suppose it is getting fabricated as a slow device, okay, both of them, okay, or both of them can get faster, or both of them can no, one of the faster or slower, it doesn't matter, but no, it will either get logged on to 1 nanosecond or 0.9 second. So if you are going to take no, the worst case scenario, right, taking this as maximum in one particular path and taking this as minimum in the next particular path, that will be adding unnecessarily additional constraint in the circuit. Okay, so whenever there are modules, okay, like these two buffers which are common in both these paths, okay, either you take 1 or you take 0.8. Okay, so that is known as common path pessimism removal. Okay, CPPR. So like once you do this particular analysis, okay, after that what the tool does is it computes what are the common, it will do the computation like it did here, right? Now after that, right, see these are the common blocks. It will identify what are the common blocks there in these paths. And now if you see here 0.2 and 0.2, so 0.4, so that 0.4 will be adjusted. Okay, that means in the total slack which is available, it will add another 0.4, so that which is also available, right? You are all in agreement with this concept, right? No point taking this in one and another, because they are going to get fabricated like that. Once it is fabricated, and you don't expect that to have different delays during different at different point of time, right? Mathematically speaking, that is true for two clock edges, right? But theoretically, if I go pure theoretical way, then I can say, especially for the setup time, okay, in the one clock edge, okay, this could have a delay of, in the second clock edge, it could be 0.8. Okay, the reason is there could be VDD variation, right? There could be a temperature variation, correct? So those variations can come. So theoretically, still even after fabrication, this difference can be there. But for today modern processors which are operating at gigahertz range, right? So between two edge of the clock, it's only a few nanoseconds, right? So within those nanoseconds, okay, there can't be any significant change in temperature, or and since most of the VLSI circuits you have an proper regulator, and unless there is a very huge load switching, you can't expect a significant VDD variation also, and hence even if it is two consecutive clock signal edges, still you can assume that it will be either 1 or 0.8 and not the other way around, where you take different values for the launch path and the capture path, and hence the tool would do that adjustment. What the tool is, first it would run a normal STA, and then it will see what are the blocks which are common in both the paths, and this difference, that CP clock path pessimism removal, okay, that adjustment is done. Is this concept okay with all of you? Have you understood? Is it okay? Because there could be some questions in the exam also to solve these kind of things. Is it okay with all of you?
So this 0.4 will be added to slack?
Yes, additional slack will be available.
Okay.
Right? Okay. That is one way of doing it. All right. Otherwise, we will stick to that. That once you compute the slack, you add additional 0.4 to adjust the slack, or in both the when you compute the slack, in both the places you take either of these value, 1 both, or 0.8 both the places. Don't take one combination of these two. Okay. Yeah.
So, once again, can you just explain like how 0.4 is coming, like
See,
to adjust?
here additional 0.2 has, for each block additional 0.2 has cropped in, right? So here there are two such blocks, 0.2, 0.2. So that 0.4 has come from there. Okay.
What is plus T is minimum clock?
So when we do the time analysis, setup analysis, you need to put T, right? Clock period T also, right? In this path. When we do the slack, when we did this slack, this 100, we put, right? That is that T. Okay. Right, and there is something known as clock reconvergence, no, pessimism removal, the second part. Now many a times, okay, there could be a mux in the circuit, and this is one clock, and this is the second clock path. So for different conditions, okay, this clock might be used from this path or this path. So the mux would select this, either this path or this path, okay. Based on like probably it could be for day operations and night operations. This path is selected. This is just a random example. So there could be multiple clock paths and which are selected through mux, and that mux is controlled by signals which is not purely dynamic in nature. That could be based on other environmental conditions or operating conditions, okay. Say it is being operated on a laptop, or it's been operated it's been operated on the main power supply or a standby power supply, internal battery, things like that. So there could be some reasons for that, right? So if there is a mux, so in this case also there is one path here, and there is a second path here, right? So if you try to take this path right, so then there are two blocks coming here, and there is only single block coming here, right? So in this case, right, so for one path, and if I take the fastest only single path here, and for the second I take this path where there are two blocks here, again that will be unnecessarily putting additional constraints, because generally these mux will not be operated that frequently, right? It is for a specific set of conditions, okay. It could be for winter operation and summer operations, right? So so you can expect that either of one of these paths only will be taken. So in that case, only one path needs to be considered between these two, right? Either you take this path or this path. Don't take both of them together, right? So it won't actually make a difference in this circuit, okay, because this clock starts from here. So all our computations of slacks won't matter, right? But it will only make a change if for one path, if you are taking here or if you are taking here, right? Then it induces an error, right? Pessimism into the analysis, okay. As long as you are taking either this or this, right, only one of the conditions here, the clock is coming at the same time, so this analysis won't get disturbed, okay. You will get a realistic analysis, okay. You will add unnecessarily more constraints only if you consider this for in one of the capture path and launch path. If you consider these paths, different paths, only then. So this is known as a clock. So if you see here, it is an 0.8 and 0.8 and 0.8 is an 2.4. So this is an 1 plus. So here also you can do the computation. 0.8, 0.8, 0.8, and how is it coming to 1.4? Can you just have a look? So if the fastest path, which if I take here, it is 2.8, and the most delayed path is 1 plus 1 plus 0.8, 2.8, and fastest will be 0.8 and 1. So if you take the difference, you will get this, right? So you need to adjust that also, okay. So you have to do that. So this is known as so this, both these things also after doing the STA, okay, these kind of pessimism has to be removed. So the tool does that. It will identify which are the common blocks, and it will do that, right?
Can you please explain how that comes out?
Pardon? we'll talk about through one example. Okay, let's see. I think that will be more clear. Now let's take this particular example out here, right? So I have an clock coming here, right, for the setup. Okay, 20 nanosecond, right? So this the first clock. So this data is going from here to here, 5 nanosecond, right? Worst case data path I am talking about. 5 nanosecond, 4 nanosecond, and 3 nano. So 5 plus 4 plus 3 is how much is that? Okay, 12, right? And also the clock is coming here, okay, and I have a feedback path here, right? I have a feedback path here. So once this clock is triggered here, data will change here, and that data needs to be settled here, right? And here, what is the delay here? So there are two data paths. Okay, so this is one data path, okay, coming here. The second data path is through this its own feedback path. So here it is 6. 6 plus 4 plus 3, that is 13. So this is the path, data path which has got more delay. So in fact, I will not consider this delay, rather than I will consider this delay. This is right. So this is a more crucial thing for setup analysis, right? Now when I consider this particular data path, now if I talk about the setup path, this is the clock which is going, and then this is the fastest I am taking, 2 nanosecond plus 2 nanosecond, right? Plus the setup of 3 nanosecond, right? Now for the data to get triggered, now first the clock has to come here. Now I am taking delayed, okay, without clock pessimism removal. If you do that analysis, then 3 nanosecond, and 3 nanosecond is the delay in these two inverters, and then this data comes from here to here, which is 6 plus 4 plus 3. Okay, so I get 2 nanosecond. Okay, that is the setup slack. Is the first line clear to all of you? Why I am not taking this particular path? Because this path has got in the setup thing, this has got greater delay, this particular loop, right? And that is why I am taking this particular loop into consideration, right? So now if I apply the pessimism out here, right? Because this is common now in the data path as well as the clock path. Okay, so these two blocks are common. So if I take 2 plus 2, 2 plus 2 in the first here, and 3 plus 3 here, it is going to add pessimism. So I can remove this, right? I can put 2 plus 2 out here, right? So this is with the CPPR adjustment. Okay, so that is how I compute this, right? So is it understood by all of you? So whatever is the common blocks which are there in the data. So this is another example where with the feedback. Okay, so not necessarily the launch path.
Sir, can you repeat?
Yes. So not necessarily the launch path and the capture path have to be different. Okay, in this example we see this is the launch path and this is only the capture path only, capture flop also, because the same data has to come from here to here. So this delay is more out here. Okay.
So why these two terms are added like this? The highlighted red terms, 3 plus 3 and 2 plus 2. Why it's in data
this is the common. This is the common right thing available. So first, without taking CPPR, right? Even though it is in the common path, okay. Here I have taken as an 3 plus 3. Right? Here I have taken 2 plus 2 here, right? For the clock path, right? Now it is taken as 3 plus 3. Now it is the 2 plus 2 is taken here, 2 plus 2 here. So that is the adjustment which has been done. Is it okay?
Sir, question: when you have this loop,
Sir, Setup for setup path, I'm not able to understand how this 3 plus 3 plus 6 plus 4 plus 3 is taken for like the data path delay.
Say at t is equal to 0, right? Suppose at t is equal to 0, this is going high. Okay.
Okay.
So
Okay.
when is the next data going to? When is the next clock going to come here? T equal to 20. Okay.
Yes.
T equal to 20 plus no, next. I'm just talking about the clock, right? 20 plus fastest clock is in the next clock. I'm taking only delay of 2 nanosecond, and a whole time I'm reducing 3.
Okay.
Okay. Now I am taking the fastest data path. Okay, right? No, the slowest data path. Okay, so one data will come from here to here. Okay, right? What is the time that it will take? 5 nanosecond.
Yes.
Correct. And then 3 nanosecond, 2 nanosecond, right? No, 5 nanosecond, 4 nanosecond, 3 nanosecond. That is one way, right?
Yes. Yes.
There could be other path also, right? In this case, right? This data from here at t is equal to 0, it was triggered, right? Before the next clock, right? This there is one data which is coming from here, right? So when will that data get settled? Now let's consider t is equal to 0 here, right? Then I am taking the least path, the most slowest path. So for data, so 3 plus 3, then this will get triggered. It is 6, right? Plus 4 plus 3.
Yes.
Is it okay?
Okay, sir.
Right? So this data is reaching with respect to t is equal to 0. Consider that at t is equal to 0, there is one trigger, and at t is equal to 20, it is the second trigger, right? So both of them is going to change this data here, right? The final data will be just 1 second. Hello. Hello. Right. So you need to take you have to consider for the setup the worst case scenario. So this is the worst case scenario. Now in this worst case scenario calculations, right? We assume that the next clock for these two blocks, okay, in the first we took as 2, whereas for the data we took it as 3, right? So that is why we have added some pessimism there. Now to reduce that pessimism, now we take it as 2 and 2 here. Is this okay with all of you?
How is -3 is there, sir?
This -3 is the hold time, setup time. Setup time of this. This data needs to be settled before the setup time, right? So this -3 is the setup time.
Sir, whenever feedback is there, we have to take the data path through the feedback only, or
no.
we are assuming...
No. Suppose there is one more block here, right? Right. Suppose there is some more combinational blocks here where the delays. Now in this particular case, this has got larger delay. Now if there are some more combinational blocks, if this has got greater delay, then we'll talk about that, right? You have to check all the data paths which is coming here.
All possible paths we have to check. Whichever is the worst path, we have to take.
Yes, we have to take that. Okay. Is it okay with all of you? Right. And for the hold slack requirement, if you see here, right now it is 4 plus 3 plus 2, the data. Okay, now this is the fastest path. Now I take the fastest path. This is the slowest path, but fastest path is a single clock is going out here. Data is going to come here at 4 plus 3 plus 2. Okay, fastest way the data is coming. Now this is a different path here for the fastest path, right? And the clock is the slowest, 3 plus 3 plus the whole time requirement of 2. So there is no violation here. So is it okay? Now if I have to find out the T minimum, this I have taken 20. Now I found that the slack is 2 out here. So so minus 2, it is 18. Now if I consider CPPR, then I can do 20 minus 4, which is 16. So it will be max frequency will be 1 by 16. Is it okay? Is the thing clear to all of you? Okay.
Okay.
Yes, sir.
Okay. So now, for when we talk about a module, okay, with a combinational block, there could be several inputs, and each path may have different delays. Okay. So for example, this we studied in our VLSI class. Like when A is switching, when B is switching, the delays could be different, right? If both are switching, so for different patterns, okay, because the threshold voltage M2 suffers from body bias, M1 doesn't suffer from body bias. So these issues we study in our VLSI class, that for different input switching patterns, the delays could be different, right? Similarly, when we do the sizing, right? So we studied the shortest path sizing, in which we did all this sizing, and then we considered the worst case and the best case, right? So for different input parameters, right? So the worst case, so the delays may be different, right? So you could just to recall that similarly we did shortest path, and then we did the worst case path, and in both there was one best case scenario and the worst case scenario, and they were different, right? So in short, I can say for any module, right? Okay, there could be something known as contamination delay, which is the minimum delay, and which is known as contamination delay, and then there could be a maximum delay, okay, which is known as the propagation delay, right? So contamination delays can cause hold violations in the next part of the circuit, and propagation delays can generally cause setup violations. Okay. Now this is one of the ICs, right? Specifications, and 4 input, and it is an quad NAND 2 input NAND IC. Now if you see here, these are the kind of delays which are specified. Okay, so it is dependent on voltage and temperature. This is the max delay, and this is the minimum delay, right? So that is why when we do an STA analysis for each of these gates, you have to take into consideration all these things. So the delays are dependent on VCC and temperature and the process. So all this data has to come from the fab lab, right? So these are known as timing arcs. So this is an 2 input NAND gate. So if A is changing here in this path, this could have a different delay, this could have a different delay. Okay, that is also possible. This is net arc here, so it's a single net. So so there is a single arc there, right? And these are some definitions. Unateness of arc. So a positive unit, it means that if the input is rising, if the output is also rising, then we call it as a positive unit, like for an AND gate, for example, right? If it is falling, it will fall, right? If it is rising, it will rise. Okay. So negative unit means if the input is rising and the output is falling, then we call it as negative. So it can happen for inverter, NAND, and NOR, or you could have a non-unit, and that means when the input is rising, output can either rise or fall, right? And that depends on the other input. Okay, for like example, for an XOR gate, if B is equal to 0, A gets replicated towards in the output. If B is equal to 1, you get A bar at the output, right? So that is known as a non-unit. These are some definitions. So when you have these blocks like this, right? So when we do the STA analysis, suppose only one delay is given out here, right? So there are multiple paths available here for data to reach this clock. This is the launch flip-flop, this is the capture flip-flop, right? So this is path 1 and this is path 2. So I take and compute these delays in path 1, I compute the delay in path 2, and from there I max delay and the worst delay and the best delay, not best path and the worst path, okay, I compute. So I use the worst path for my setup slack and the best path for my hold slack, okay. So this is how I do. Now suppose from the tech library which has been given by the Fab Lab, if the rise times and fall times are specified separately for each of these gates, okay, in that case for each path, okay, I compute the rise delay, fall delay, rise delay, fall delay, and then for the setup slack I take the max delay, okay, irrespective of rise and fall. So here if you see 11, 13, 12, 12, so 13, okay, doesn't matter if it is rise or fall, okay, because when I am doing my STA analysis I have to cater for both these delays, okay. So worst case scenario is 13. So for my setup analysis I will take 13 as a max delay constraint, okay. Whereas the minimum path now here 11, 13, 12, 12, 11. This is the fastest, okay. It doesn't matter if it is in rise or fall. So I take this as the fastest path, okay. Is this okay? This is depends on what type of data is available to you from the Fab Lab, okay. If this kind of data is available, this is what I will take, okay. Is it okay till here? Okay. Now say there are two libraries available from the Fab Lab, right? Okay, it says okay for certain conditions either this can get fabricated like this or like this, right? In that case you have to separately compute for both the libraries and then take the worst case scenarios, okay. So this is this is another example where there are two libraries. If you are not sure of which library you are going to use, okay. But if you are sure that you are going to get it fabricated only with one library, then this. But if you are not sure, okay, finally that what library it is going to get fabricated, then you might want to do an STA analysis of this, okay. So this is another way constraint which comes in. These are all based on the data which is available from the Fab Lab. Now this is like this is known as path-based design, in which the delay of this path and this path, from because this is one input, this is other input. Okay, this input can have and different contamination delay and propagation delay. This input can have a different contamination delay and propagation delay, right? So for each path, I compute the max delay and the min delay separately. Okay, so this is one path, this is the second path, and C is the third path. So for each path, I will compute separately, and then I take the worst case scenarios for each of these paths. Okay, this is known as path-based delay. Is this okay with all of you? Is it understood? This is known as path-based delay. So this is slightly time consuming. So we have something known as a graph-based delay. Okay, in this what you see is instead of computing several times, okay, what the tool would do is from this data, okay, it will compress the data like this, right? So it will take the best case and worst case. Okay, so the dependency on the input is eliminated, and just for the gate, okay, 10, 12, 12, 14. So 10, 14 is taken here, right? So similarly 11, 13, 13, 15. So 11, 15 will be taken here, right? So this is a single, so it comes as it is. So you take, what it does is the tool would make these gates, okay, delays independent of the input pattern. Okay, so it will compress this model of this gate like this. Why it does this? So it will save a lot of computational time. Okay. Right now we are only speaking about 2 gates, 3 gates. Okay. Now if you consider a circuit with 1000 gates, and for each of all these gates, if you start taking two paths, so you can assume how much more time it would take, right? It will take a lot of time. Now, and hence it makes sense to do like this. Okay. Now this becomes, obviously this becomes much faster. Now it has become much faster out here. Now if I do an analysis of the graph based method, this is the for the graph based method. Okay, a max delay and the minimum delay. This is the top one, which is shown in red, is just for the single path. Okay, AY. This is using the path based, and this is the graph based. So obviously you will see this here. You get an answer which is slightly bloated up, right? It is slightly pessimistic, right? Obviously, this is more precise, and it helps you obtain a more realistic value, but this is going to consume lot of time, right? If you consider like this, but this is going to make the entire simulation process simple and faster, but obviously you will be overdoing a little bit, right? The margins which you will take will be slightly on the safer side, right? So there could be some pessimism in this issue, right? So if you see here, so you can I'll share these slides. So even for the other paths also, you will see it is 40 and 32 when we do the it is for the B path. Okay, BY path. So it is 40 and 32, but whereas when you do the graph based method, it is slightly on the higher side, right? 42, and this is also faster, right? 32 has come to 30, 40 has come to, so this is actually a subset of this. Okay, here also this is a subset, this range is subset of this range. Here also this range is subset. Here in both the cases, additional 2 nanosecond, 2 picosecond additional has been inserted. Okay, but that simplifies the overall analysis, right? So similarly, this is in a third case. Here you will see 4 picosecond in the third path. Additional penalty we are inducing. Okay, for the sake of simpler and faster simulation. So right here it's not making a difference. So, but overall this will be a subset of this. Okay, so you are not going to make any critical error. Okay, you are only making an error on the positive side. Okay, so that is the advantage of doing this. Okay, now most of the tools they provide an advanced on-chip variation thing, right? What it is like this is known as the depth, right? So here this is one path. Okay, where I have 1, 2, 3, 4, and 5. There are 5 different blocks, and here this is only there are 3 different. So this is known as the depth. Okay, so here the depth is only 3, right? And the total distance here is 1000, right? So as you what it does is from the fab lab you have an data. Now for example, say this I have an 1, 2, 3, 4, 5, right? So if I put a maximum say 10% variation everywhere, right? So it will give me some kind of variation. It will cater for some percent of variation. Now suppose I have 10 blocks. Okay, so should I put 10 everywhere, or since the possibility of that all the 10 will have maximum 10% variation will decrease?
Yes.
Correct. So as you keep increasing the number of blocks, right, and also the distance, it is not necessary that you keep applying the maximum delay everywhere. Okay, if it is a short one, okay, you do that. But as you keep increasing the number of stages, okay, so rather than applying the maximum worst case scenario, like the maximum percentage variation on each of the blocks, you can slightly reduce it. Okay, so that's what this kind of table will be given by the Fab Lab. Like for example, if it is only 3 stages, okay, so the delay per unit is 1.142. Okay, now if it is 5 stages, okay, if it is 5 stages, then per unit delay you can take as 1.24, right, rather than taking 1.142 into 5, right, the total delay, I can take slightly lower delay, because the probability of each of them get fabricated at the extreme 10% is much lesser. Okay, so that is known as advanced. So this kind of data should be available to the tool. Okay, so unless this data comes from the Fab Lab, you can't just arbitrarily fix these. Okay, so this kind of, once this kind of data is available, then it can do an more like it is kind of removing of pessimism, right? So simply blindly putting 10% in one chain, plus 10 and putting minus 10 in the other chain, what it does is, as you keep as the depth increases, right, you reduce the unit delay slightly, because the probability of each of them having the max delay decreases. Similarly, if you go vertically down here also, right, if the distance increases, right, then the delay could increase, right. So that is taken the other way around. So this kind of table needs to be made available, then and the tool makes use of this particular lookup table to do the STA analysis. Okay, that is known as advanced on-chip variation. Okay, and I will so these are some of the limitations. Okay, so for 40 nanometer technology and below, there are certain issues with this. So we use POCV models generally for technology below 40. What is POCV? That's the last thing which we'll discuss today in the next slide. Okay, so this is known as parametric on-chip variation. Okay, so I'll explain that in the next slide. Suppose this is the nominal value or the central value on a delay of a particular gate. Okay, so generally, okay, this will be the distribution curve. Like if the standard deviation, right, if you consider the standard deviation of so what is standard deviation, right, you have that from the statistics, right. So 1 sigma is the standard deviation. In 1 sigma you will find 65% of the fabricated chips would get covered, right. If you take 2 sigma, then 95% of the from plus 2 sigma to minus 2 sigma, 95% of the chips would get covered. And if you take 3 sigma, right, plus minus 3 sigma is generally known as 6 sigma. So 6 sigma is a very good figure. Okay, it would cover 99.7% of your chips. Okay, so this is a very good figure, right. So what you do is, in your STA analysis, the central value will be given by the Fab Lab, right, and sigma which you need to feed is a variation, which is a variable available to the designer when you do the STA analysis, right. So depending on what kind of accuracy you require, you will set the value of sigma, right. So if you put 6 sigma, right, that is plus minus 3 sigma here. So if you write this on a 6 sigma analysis, so if you put this, you can be more or less sure that no point in going beyond that, because it is overestimation. So 6 sigma is generally considered very good, right. So you could go for 2 sigma also, right, if you have that kind of confidence on your Fab Lab. But otherwise 6 sigma is the standard which you go. Okay, so that is about a parametric on-chip variation. Okay, now in the next class will stop it here because I don't want to confuse two different concepts. Okay, till now we were talking about single flip-flops in a big circuit. Okay, we have not analyzed a circuit as a whole, right? So so there the definitions will slightly differ. As of now, the STA analysis what we learned today is for each flip-flop. So the STA analysis needs to be done for each flip-flop in the circuit. Okay, whether the hold and the setup constraint for each flip-flop is being met or not, right? So and each flip-flop might have multiple paths. So all those paths, like in this, like we saw some examples. So all these paths for each of these flip-flops have to be analyzed, and the worst case and the best case scenarios for the setup, the worst case scenario will be taken, and for the hold, the best case scenario will be taken. So these things needs to be done. Okay, so we'll stop it here, and then we'll in the next class. Before we move on to a new topic, I just want to cover a small aspect of when we look at a full module. Okay, how the analysis would change a little bit. Okay, so I'll cover that aspect in the next class. Okay, thanks a lot.